Okay, welcome to today's lecture series. In this course, we have been talking about manipulated robots, talking about mobile robots, a little bit about quadcopters. We've been talking about kinematics, dynamics. We have talked about control, and of course, modeling, simulation, all of that we have done. And then, what we haven't said much about what are the sensors on the robots, okay? And the next 2 or 3 lectures will be on sensors. And let me go to here and also mention to you that in the book doesn't have much about sensor, only on vision, which is only one part of the sensing issue. You know, sensing can all not be just looking, but you're hearing and many other issues. They've got the 5 chapters on that, which unfortunately we're not going to get much time to do much on it. But some of the elements of these 3 lectures are going to be vision-based, image-based. So if you want to continue in this area and this field and working with image processing and vision applications, you will be, I think, well served if you look at these chapters. Of course, one of your groups, which I don't see them in the class today, are already doing vision feedback. Remember the work that Kartik and Nick and Nico did, progress report they did earlier with a camera from a quadcopter looking down to 3 robots, mobile robots, and basically that vision feedback was used to control those 3 robots together. So let's look at overview of our sensors for robotics. The content of these 3 lectures are already, or should be already, on Dropbox and Blackboard, and you can download them. So what makes a machine a robot? You sense, in this case, a human driver is behind that forklift and knows where the truck is. Where is that truck? The driver in here and wants to ask himself, where should I dig? Okay? So then the driver has to plan where to dig and know where the location of the truck is, and finally does the action. You act on the environment and lifts a big chunk of dirt and puts it into the truck. So in this case, the sensor is really the human being, the driver, which senses the distance from where he sits and where the fork is and the truck, and where particular dirt he wants to dig and pick up. So if you have a manipulated robot, the robot wants to basically say, what is my angle? What is the state of do I need? Okay, this is some internal information on this robot itself. Okay. So what is sensing? Sensing is collecting information about the world. It is an electrical, mechanical, chemical device that maps an environment attribute to a quantitative measurement. So you may have a distance in meters or feet. You may have some kind of light intensity in some appropriate dimension. You may have, let's say, amount of temperature, pressure, humidity, etc., etc. They all change to some kind of voltage or current where you can use in real time. Okay? Attribute mixtures often no one-to-one map, that means hidden state in environment. So you have situation where, especially for mobile robot, you are in an environment where you need to know where you are and where to navigate. Localization is something which we talked about last time. So all of those decisions and those attributes and those issues with the robot, the first item of business is sensing. So each sensor is based on what's called transduction principle or transducers, which converts energy from one form to another form. Okay. So as you know already, the mobile robot needs to know where it is. So where am I? You need to be able to locate yourself. Okay. And last time we mentioned that you, with the help of landmarks around you, fixtures around you, and estimation theories like Kalman filtering, you can actually try to minimize the error of what we call odometry error. Okay, where you should be and where you actually are. Okay, there are always a discrepancy there. So robot needs to detect obstacles around it. Okay, we'll get to the different sensors which will do that, and it needs to detect an obstacle and try to, then that decision, that information, that piece of data is going to help the brain of the robot, the controller of the robot, to avoid the obstacle. So robotics is everywhere, as I think you already probably know. It has a big effect on agriculture. Okay, and these days you can program your autonomous harvesting machine. Okay, this machine is automatically harvest in the harvesting field, and the robot needs to know where is the crop line. Okay, it's not going to harvest anything in this area, so it has to work very carefully through its sensing to harvest when it should do that. Or you may have a fork lift here, and as you see, it has a couple of blades, and those blades needs to be exactly fit into the holes here to be able to lift something. Okay, so those are again for autonomous material handling. Or you could have vision. You could have a camera looking at human face or a skin tone. A skin tone is the most important of many images in image processing. Okay, a skin tone is the part of the body where, especially the face, is that you can recognize somebody. Okay. What are the different types of sensors? And there are numerous of those. One categorization is active versus passive. And active sensing is send signal into the environment and measure the interaction of signal with the environment, like the radar, like the sonar, which we get into details of it later on. Okay. Passive sensors are those which record signals already present in the environment. For example, there is a video camera in the corner of the room, and it already has images, and then the robot will make advantage of that information, which is outside of its own internal domain. You could also classification them by medium use, based on electromagnetic radiation of various wavelengths, or based on vibration in a medium, based on concentration of chemicals in the environment, or by physical contact. Okay, a lot of end effectors are manipulated, 2 or 3 or maybe even up to 5 finger end effectors. At the tip of it, they are tactile sensors. which actually can touch, can feel the environment. Okay, so tactile sensing is a typical physical contact sensor. Another type category is exteroceptive versus proprioceptive. The first one deals with the external world. Want to know where is something that robot needs to know? How does it look? Is it? Can I look at through a camera? Can I send a laser signal and get a feedback, receive it back, and to find the range of that particular obstacle or what have you? And the other one is dealing with its own self. Where are my hands? For example, these can be answered by encoders and storage receptors, which we'll see later on. Or am I balanced with a gyroscope or some other inertial sensors? And these are very important, you know. Some of you may be too young to know that in the early 1980s, a lot of SUVs were running very fast in curves and would flip over. Until major companies like Ford and others figured out that they need a specific gyroscope to be put on those cars so they would stop it from flipping over with the gravitational, with those kind of gravitational issues. So gyroscope is always very good, and most of our robots in ACE labs, those track robots have gyroscopes. Early on, when I was here at UTSA, a friend of mine was president of a sensor company, and I got as a gift a lot of gyroscope sensors from them. And my students in 2006, 2007 timeframe were putting it on those track robots. So you see in some of our videos broadcast on local TV that our track robots would actually go like that and then flip over without falling up because we put the right gyroscopes on it. Another type is interoceptive. What is my first level? It is a biochemical robot or a sensor rather. What is my battery charge in terms of like a voltmeter? So these kind of sensors are ignored because it's so well known in technological field way before robots were around. So we just ignore them and we take them for granted. So these are the robots that we can purchase. In fact, if you Google any of them, the first thing they do for you is give you a whole bunch of prices to buy them. Touch sensors, I told you with tactile sensing, or tilt sensors. Encoders, which measures the velocity of the shaft of a motor, which rotates the joint of a robot. Bend sensors. There are robots which we didn't discuss too much on them, called flexible robots. All the robots that we talked about, the manipulated robot in this course, we've been assuming that the whole link is fixed and it's not bendable. Okay? There are actually a class of robotic research board. Some of my former PhD students in another university were actually working on building flexible robots. Well, the end effect, the link of it is like basically a piece of flexible, flexible metal. You could actually, it's very difficult to measure its location because you have strain gauges and many other things you have to attach to it and be able to do it. So it would be good to know when a link is being bent or not. Okay, so you could have sensors for it. Most likely bend sensors are strain gauges which you can put it on different distances on a flexible joint. Or light sensors, temperature sensors, potentiometers, laser rangefinders, and cameras. Okay. Touch sensor is essentially a simple switch. When you touch a physical environment, you push on some part of the sensor here, which when you push it long enough, this circuit will be closed, and then this spring will compact, and then you basically have a potential across this, like a capacitor, which then gives out a measurement voltage proportional to the how much you push on this gadget to sense something. Or you could have a tilt sensor, where if it's tilting through the gravity, you can figure out which way you are tilting. Encoders measure rotational motion. You know, you should all be familiar with potentiometers. I'm sure you all are. And those are voltage across a resistor, and the resistor has variable resistance, and through that you can measure a voltage proportional to let's say angular position of a motor, and so forth and so on. But encoders are much more accurate than potentiometers, and they can be used to measure the rotation of a wheel. They can also, in servo motor, used in conjunction with an electric motor to measure the motor position and in turn control its position. So it is it's a superb potentiometer, if you will, and what it does, it actually has a light source which goes from one side of the encoder, and the encoder is rotating with the speed of the motor, and depending on the frequency and the speed of the shaft of the motor, this particular device let the light go through, and then you can see what part on, what part is off. Okay, and I'll get more to it later on. I have more slides on this. So, for example, here, let's say look at a bit of sensor analysis. Suppose that we have encoder which basically has 16 counts per revolution, and suppose you have a robot which has a wheel diameter of 10 centimeters like this. How far does the wheel travel for one encoder count? That's one question you could ask. What happens if we change the wheel diameter? If we increase or decrease that, what happens? How many counts are there per meter of travel, or 1 meter of travel? So here how you can calculate. This is the diameter of the wheel, which assume it to be equal to b. And if you multiply by pi, you get the circumference of the whole. Remember your equation for the circles in your algebra? That is the circumference of a wheel. Assuming that d is 10 centimeters, c becomes 10 times pi centimeter. So you have 10 pi centimeter for one revolution. That's equal to one diameter, one circumference. You have one revolution, 16 counts. This is something which comes with the device, comes from the manufacturer of the encoder. Then if you simplify this equation, you get 1.696, almost 2 centimeters for every count. So this is one encoder count. How far is it? It's going to be about 2 centimeters. Okay. Now the next question: what happens if we change the wheel diameter? So suppose we want to 1 centimeter per count rather than 1.96. We want 1 centimeter per count. What should be the wheel diameter? Okay. 1 centimeter per count, 16 counts per revolution, becomes 16 centimeter per revolution. So your circumference of a wheel which you don't have yet should be 16 centimeter. You divide that by pi, you get 5.09 centimeter is the diameter of your wheel. So the wheel used to be 10 centimeter in diameter. If you want to have that particular specification for centimeter per revolution, then you have to buy another wheel, almost half of this one, but almost 5 centimeters. So the next question was, how many counts are there per meter of travel? Suppose we are traveling 1 meter with the robot, okay, and it takes a finite number of turns or revolutions, and assuming that you have 16 counts per revolution, how far 1 meter of travel will take you? So in this case, we have 1.9 centimeter per count, which we calculated before in part 1. We have 1 meter for every 100 centimeters. So that becomes 0.019 meters per count. Okay? And if you invert it, you get the number of counts per meter. 59 counts per meter. For every meter, the encoder will have 51 counts for you. Now, remember your physics 101, remember Ohm's law, okay? And you have, let's say, a resistor here of 1000 ohm, and you have 5-volt battery. You divide by that, you get 0.009 for your current, okay? So, in a similar way, you could have an analogy here. You have let's say, a container of water or liquid here, like a water tower. The amount of water in way up there is essentially a potential energy. Okay, you have so much weight being so far above the ground, equivalent to a voltage. That potential energy is a voltage. The amount of water going through is flow of the water is a current. So a larger pipe is less resistance, so more water. So you have a larger pipe, it goes there. So if resistance is a smaller, more current is going to go through. And if you have a smaller pipe, more resistance, less resistance, so more water, more resistance, and so less water. Okay. So it's similar to what Ohm's law will tell you to do. This is a bend sensor. It's a variable sensor which you can go through one end to the other end, and each part of it is going to be basically have a particular voltage. Again, using Ohm's law, you can move along this. Bend it here, bend it there, bend it. Wherever you bend, you have a different resistance. And that means different voltage. The current is constant, but the resistance keeps changing. Light sensor. Light sensors are sensors where you shed light on the sensor and gives you a voltage or a current. So this is how to measure the light sensor. The amount of intensity of light. Temperature or thermostat that you see it in many homes and your rooms and so forth is a thermal resistor, and depending on how much heat you put on these two sides, you will have different readings and proportional to the temperature. Potentiometer you already know. I've seen it a lot, typically looking like this, and depending on where you are moving along this winding, you have different voltages from here to one side or the other. So let's, for example, look at the bend sensor. We are given a 5-volt source. What is the minimum and maximum current that is drawn through that sensor? If the sensor is straight, it's 100 ohm resistance. If it is bent, it's 1000. So if you divide by 1000, you get 5 milliamp, that's the minimum. If you divide by 100, when it's straight, 50 milliamp. So that's the range of current which goes through the bend sensor. Okay. In this case, the voltage is fixed, the current is not. So electromagnetic theory and spectrum analysis of those also allows you to a new wave of sensors which you can use. Some are light sensitive, like eyes or cameras or photo cells. Some are based on operational principles like charge coupled devices, CCD, or photoelectric effects. Some are on IR, infrared sensitive. Those are sense heat differences and construct images, and night vision application. You could use that for night goggles, for night vision that, for example, our soldiers use that to be able to operate in the middle of the night. Okay. Radio and microwave are also allow you to have a lot of other potential. Radar is a very important class. It's a radio detection and ranging. That's what radar stands for. Microwave radar, which is insensitive to cloud. Unlike many other vision type of things, cloud is not going to affect them. You have coherent light. You have, for example, laser, which, as you don't know already, stands for light amplification by a stimulated emission of radiation. That means laser. Okay. And all photons have same phase and wavelength in the coherent light. And you have laser radar and LADAR, light and radar, combination of light and radar, which gives you an accurate ranging. So radar was invented during World War II, and lasers were invented shortly after that, maybe 10 years later, in the 1950s. Okay. And then they put it together, the two technologies became radar. Okay. And has a lot of defense applications. SICK laser rangefinder is another sensor which is commercially available, which you can put it on your Pioneer robot and things like that. Speaking of Pioneer robot that you see in this chart, we have two of them in the lab, which are not necessarily the latest one, but it's actually rather old, but they still very work. And thanks to my capable students, we have been modifying those robots and bring them up to current technology without buying a new one. Okay. And now our Pioneer robots have encoders, which measures the velocity of the wheel moving. It has sonar. You see all these 20 of them. You have 16 sonars, okay, which I'll tell you in a minute how sonar works. We also, in place of this, we have put Kinect robot cameras on it, and we have accelerometers, another sensor which measures the acceleration. We'll get to that later on. The Kabuki robots that are being used in one of the projects in the course by those students I mentioned, they have encoders on it, they have gyros on it, they have IMU, and they they also have similar to Kinect cameras on it. So yeah, they've already got 4 sets of sensors on it. Soon we are putting GPS on them because we want to move them outside of the ACE field lab into the outdoor and run them over there. There, the image processing is not going to work, okay, because of the sunshine and other things. So that works inside the lab. Outside, we're going to use GPS. And GPS is another sensor which we'll talk about. So nuclear magnetic resonance is another EM-based, EM spectrum-based heavy-duty magnetic field lines up atoms in a body. That's what they do. And now expose body to radio signals. And they can do different nuclei resonate at different frequencies, which can be measured, leading to an image. So this is what you could actually detect a person by a signature of their images and identify that somebody was running through that area of the field in, let's say, so much minutes ago or so many hours ago. Those things are solved issues. Local proximity sensors in EM, a big group of that is infrared LEDs, light emitting devices. They are cheap, they're active sensing, they have low resolution usually, and normally used for presence or absence of obstacle rather than ranging. So if you just want to know whether something is there or not, you can use a cheaper version of this sensing devices for what we call proximity. And they can also operate over a small range, not for too far away. Sonar, we talked about sonar a few minutes ago, is sound navigation and ranging. That's sonar. It bounces sound off of something, okay? Sonars are the only hope you have underwater. And nothing works underwater. GPS doesn't work, okay? But image does work, but again, you need to be able to have sophisticated image processing group. In our lab, Ben Champion is using 2 sets of cameras under the water, and he doesn't need sonar because our robots sort of cheated. We bought those robots which are tethered, so all the communication is available already. Right? Okay, goes directly to the laptop of the robot, and he's busy preparing a combination of a group of vehicles and 2 underwater robots, a ground robot, and a mechanism to pick some, identify and detect some object under the water, and send some mechanism to go and pick it up and bring it out of the water. Okay. They all measure time for reflection to be heard, gives a range measurement, and measure changes in frequency, gives the relative speed of the object through Doppler effect. I'll mention to you Doppler effect in a few minutes, maybe in the next lecture. Bats and dolphins use amazing results. Okay? So dolphins and bats work in a range where humans are not capable of doing. Okay? And if you go to any caves where the bats live, they change and move so fast that you can't even see what they're doing. Okay? And of course, dolphins are extremely smart animal, and they're much more capable. And we get to that also again later. Robots use it with less than amazing result. Okay, so the best underwater robot is what? A dolphin. Okay, and military are using it. Some military, I think our own military are using it in some way for specific applications. Like they're using dogs on the ground, okay? Trained dogs, you could do the same thing. So what is Doppler effect? Doppler effect or Doppler shift is the change in frequency of a wave or other periodic event for an observer moving relative to its source. So, observer could be sitting in this car, and it is named after the Austrian physicist Christian Doppler, who proposed it in 1842 in a meeting in Prague. So as you can see, when the source is addressed, this is how you see the wave. But when you are in motion, it looks like this. Okay? And they're not coordinated and they're not equally distanced like you see here. Sonar and IR, infrared proximity. Again, these are sonar that I mentioned to you from our Pioneer robot. What is a sonar? Sonar is a system for the detection of objects underwater and for measuring the water's depth by emitting sound pulses and detecting or measuring their return after being reflected. So, submarines use it all the time. Submarines can send a signal to the bottom of the ocean or floor, and they can measure how far they are up, where are they here, okay, in terms of ground. Unfortunately, I would imagine that Titanic didn't have a good, or at all, no sense, no sonars. If they had sonars, they would detect the body of ice within their proximity, okay? Odor sensors, senses which smell like your nose, detection of chemical compounds and their density in an area. Spectroscopy is one application of that, which are mostly restricted to a laboratory environment. You have fiber optics technique, which have recently developed chemical detection, sniffers and electronic nose by way of wet chemistry on a chip. Okay. You have actually sensors which you could call them artificial nose. You could put it on a robot and send the robot into a minefield and try to sniff existence of a mine under the ground level. Okay. No major penetration in robotics yet. Applications are vast. Okay. Touch sensor. We talked a little bit about it. Whiskers. I'll get to whiskers also soon. Bumpers, which you bump into something and you know that you've touched something. A whisker, it's like a whisker of a cat. Two pieces like that going the two sides of the robot, and it hits the wall, and you know you're so far from the wall. When I first taught this course 10 years ago, I actually gave a small robot with two whiskers in the front, three-wheel robot, which you still have some of them in the Bobot or something we call them. And every two students had one robot, and they start from scratch in the course, building it from ground zero, and then at the end of semester, each team of the students, a class like this, they put their robots in a maze, and we measure how far it takes to get out. And then we gave the award to that person. In most time, we didn't have any winners. Okay. But occasionally we did have winners. Okay. So it can be used for closing or opening of a switch. It can be used to change in resistance of some element, change in capacitance, or change in spring tension, and so forth. Again, back to proprioceptive sensors, encoders, and potentiometers. These are, as we saw before, measure angle of turn via change in resistance or by counting optical pulses. That's the encoder, optical pulses. Gyroscopes measure the rate of change of angles, and some are fiber optic, newer or better ones are those magnetic, which is an older one. Compass measures which way is north. A lot of times we do put a compass sensor on the robot up in the front, and some of our robots which we built have done that before. And then GPS, Global Positioning System, which I'll get into details of it maybe in the next lecture, how it works. So this is some of those proprioceptive sensors. So the question is what sensor to employ? For mapping, if you need for mapping, you need ranging, laser, sonar, IR, stereo camera pair, salient feature detection, doors using colors and so forth. Depends on your application and your mission or your research, you have to choose appropriate sensors. The factors that you need is accuracy, cost, information needed, and so forth. Of course, in a university environment, the cost is important because we can't afford very expensive devices. Okay? Although I was able to spend quite a bit of money when I first came here because of the what's so-called startup fund, and I used to spend $16,000 on a sensor, for underwater research of PhD advisor of Ben, who is now here. I'm hosting the son of my former student, or the student of my former student, I should say. So, where do we put them? Well, that's another question you need to ask. Where do you need to put them? On or off board? You want to put them on the robot, or you want to put in the environment where the robot is moving? And sometimes both possibilities. You want to use odometry versus localization using beacons. If it's on board, where would that be? Okay, what kind of arrangement would be most appropriate and optimal? So these are some of the sources. Website, you can look at those websites. And these are some of the questions I want you to review the slides you just saw and try to answer these questions. Okay? It's all relevant to what we just proposed. Okay? And this is a student of mine never knows when I'm teaching. Okay? So, in any case, to pay attention to that, you never know, it may pop up in the finding. Okay? Review this very carefully. Okay.